Today on Macaulay Math, we're talking inverse trig functions. Intro. Okay, good day. I'm Professor Macaulay. This is Math 150 Pre-Calculus, Lesson 22 on inverse trig functions. Our goals for today: we're going to evaluate inverse trigonometric functions. We're going to evaluate a composition of trigonometric functions. We're going to solve problems involving inverse trigonometric functions. At the most basic level, inverse trig functions are used to solve for unknown angles in a right triangle when two or more sides are known. But due to the periodic nature of trigonometric functions, they are not one-to-one. Therefore, the domains of trigonometric functions must be limited for us to create inverse trig functions. This creates some necessary nuance when using them in application problems. Today, we will discuss those nuances and learn how to get around them. Let's get started.
Okay, let's start with some definitions here, and we're just going to define inverse functions. And so if you see on a test either arc sine x or sine inverse x, that is referring to the inverse of the sine function. Same thing with arc cosine and cosine inverse x, and arc tangent and tangent inverse x. What are we going to use inverse trig functions for? Well, let's take a step back and look at what trig functions actually do. The regular trig functions, sine, cosine, and tangent, are used to find the ratio of two sides of a triangle. So when you say that the sine of pi over 6 is equal to a half, that means that the ratio of the opposite side to the hypotenuse of a 30-degree angle or a pi over 6 radian angle is going to be 1/2. The inverse trig functions are used to find the angle of a right triangle given the ratio of two sides. If you take the inverse sine of any ratio, it will give you the angle measure of the ratio, with the numerator being the opposite side and the denominator being the hypotenuse. Let's recall a few things about inverse functions. Regular functions must pass a vertical line test. Inverse functions must be one-to-one. So let's talk a little bit about one-to-one functions, and we're going to use a Desmos demonstration here to discuss one-to-one functions. Note, none of the trig functions are one-to-one. We are going to limit the domains for all of these to force those functions to be one-to-one. Let's go to Desmos and review what a function is and what a one-to-one function is. Okay, so here I have a simple function. It is 1/4 x squared. It's just a general parabola. It goes through 0, 0. It is a function, and the reason that it is a function is because it passes a vertical line test. So if I go x equal to 1, it should give me a slider here, and you will notice that if I have that vertical line test, no matter where I go along the domain of f of x, along that x-axis, my vertical line only passes that red curve in one point. That's what makes f of x a function. F is not a one-to-one function. So if I put in a y equals to 1, and let's turn off this line, the red parabola does not pass a horizontal line test. So this horizontal line passes the red curve through this point right here and this point right there. Clearly, the original red function is not one-to-one. So what can we do? Well, we could limit the domain. And the way that you do that is you go bracket x greater than 0. And this is not the only way that we could limit the function to make it one-to-one, but we clearly now see that it passes that horizontal line test. And if we bring in the vertical blue line, it still passes the vertical line test. So we have taken a function and we've limited its domain so that it passes both a vertical line test and a horizontal line test, making it one-to-one. So let's look at trig functions. So if I go y equals sine x, and let's blow this up just a little bit. Let's go from -2 to +2. And let's put back in that x equals 1. Clearly, the black sine curve is a function because it passes that vertical line test. It is not one-to-one because it does not pass a horizontal line test. There are many places that it can cross that horizontal line. So what we want to do is we want to take this sine function and we want to limit the domain so that it does pass both the vertical and the horizontal line test, but I get both all of the possible values in the range. And the way that we do that for sine is to go from -pi/2 is less than x is less than +pi/2. And so here I get all of the possible outcomes of the sine function, and we go from -pi/2 to +pi/2. And all three of the major trig functions have a domain limitation. And so let's look at those domain limitations. Both sine of x and tangent of x go from -pi/2 to +pi/2. Cosine goes from 0 to pi. And the reason that is, I will go down to the next slide and show you. If I went from -pi/2 to +pi/2, I'd only get the positive values in the range. And since I want to have all of the possible values in the range, I move it over, and here I go from +1 down to -1. So that is why that domain is different than the other two. And then your trig function looks like that. Y equals tangent x from -pi/2 to +pi/2 will be this solid blue line. And then the inverse of that will go from -infinity to +infinity. But the y values still go from -pi/2 to +pi/2. All right, trig functions and their inverses. Now, from a lesson earlier in the year, we know that if we take a function and we compose it with its inverse, or if we take the inverse of a function and compose it with the regular function, they should both reduce down to x. That holds true with trigonometric functions as well. So if I want to get this theta by itself, since I have tangent, I'm going to do the inverse operation. Now you guys have been doing this since probably 5th or 6th grade. What you do to one side, if you do it to the other, you keep the equation in balance. And so if I had 3x plus 2 equaling to 6, we know that we would do subtraction from both sides because the inverse operation of addition is subtraction. 3x equaling to 4. We have a multiplication here, and we're going to do the inverse operation, division. Division is the inverse operation of multiplication to get x by itself and get a result of 4/3. Now, trig functions are the same, but you have to remember that the tangent of theta is not tangent times theta. Tangent is its own operation. Multiplication is an operation. Tangent is an operation. They're different. Since they're different, they need different inverses. So here's what we're going to do. We are going to take the inverse tangent or the arc tangent, that they're the same, of both sides. So I'm going to have tangent inverse of the tangent of theta is equal to the inverse tangent of 4/7. And just like addition and subtraction cancel out and multiplication and division cancel out, inverse tangent and tangent cancel out, leaving me with theta by itself and the inverse tangent of 4/7 on the right hand side. Okay, evaluate the following inverse trig expressions. So here I have arc sine of 1/2. Now remember, sine are your y values. So what this literally says is what angle measure gives a y value of 1/2 on the unit circle. Now there are two answers to this. There is a half right here, and there is a half right there. So there are two possible solutions, pi over 6 and 5 pi over 6. But here is the problem. When I go back up to sine, sine is limited from negative pi over 2 to pi over 2. So the only values that I can use on the unit circle are from here all the way around to there. So 5 pi over 6 is not in this domain. So my answer to this problem is going to be pi over 6. Now, to solve the next one, I need to erase this. And let's clear this out as well so we can see everything. Because arctangent, square root of 3 over 3. Clearly, none of these values is square root of 3 over 3. But we remember tangent by itself is equal to sine over cosine of theta. And so what I'm looking for is a ratio that's going to give me square root of 3 over 3. Now, the ratio of square root of 2 over 2 and square root of 2 over 2 is not. 0 over 1 or 1 over 0 is not. So the only values that we're really going to be talking about is either pi over 3 or pi over 6. We're not going to be talking about negative pi over 6 or negative pi over 3 because one of these two values in each case is negative, so I'll have a negative over a positive. That would give me a negative result, and since this one is positive, I know I have those two values. So let's just take a guess and make it this value right here. And so if I go 1/2 the y value over square root of 3 over 2, well, I got a fraction divided by a fraction, so I will go 1/2 times the reciprocal of that, which would be 2 over the square root of 3. My 2's cancel. That leaves me 1 over the square root of 3. Can't leave a square root of 3 in the denominator, so I have to multiply by the funky 1, square root of 3 over square root of 3. 1 times square root of 3 is square root of 3. Square root of 3 times square root of 3 is just 3. So this value right here gives me a ratio of square root of 3 over 3. The angle measure that corresponds to that is pi over 6 again. So in each instance, I get pi over 6. All right, next example. Solve the following for theta. I've got the tangent of theta is 3 over 4. And remember, what we can do here is we can set up a right triangle to represent this situation where this angle right here is theta. Now, I don't know what the actual lengths of this triangle are, but I know that the opposite side to the adjacent side have to have a ratio of 3 over 4. So we're just going to let these numbers stand in. And if I take the arctangent of both sides, so I go tangent inverse of the tangent of theta is equal to the arctangent of 3 over 4. And after we do this a couple times, you could probably skip this intermediate step. But that gives me theta by itself. And I've got my tangent inverse of 3 over 4. Now in the last problem, we found a ratio that was on the unit circle. We're not going to find a ratio on the unit circle of 3 over 4. So we're going to have to use a calculator to do that. So let's go back over to Desmos, and if I hit this little wrench, you'll see here at the bottom I have either radians or degrees, and I'm going to leave it in radians for this problem. And we are just going to type in the tangent and then shift 6 to get it into an exponent, and then just a -1. And Desmos understands that we're not raising to the -1 power, we're actually using the inverse. And then it's 3 over 4. And I get 0.64, and then that will round up to 4. So 0.644 radians. And we are labeling that appropriately. All right, next it says we want to write theta as a function of x. And so when you say theta as a function of x, that literally means that theta is the function and the independent variable is going to be x. So we want theta by itself and only the variable is x on the left-hand side. So I look at what I have here. This is my angle. This is my hypotenuse. And this is going to be opposite of the angle that is in question. So if I have theta opposite and hypotenuse, we're talking sine. So I've got the sine of theta is going to equal the opposite over the hypotenuse. In this case, the sine of theta is unknown. The opposite side is going to be 12. The hypotenuse is x. And since I want theta in terms of x, I almost have that. I don't have theta by itself. So I'm going to take the arc sine of both sides. And that will give me theta is equal to the arc sine, the inverse sine of 12 over x. So now I have theta as a function of x. Theta is by itself. The only variable on the right-hand side is x. I'll put a box around that and call that one done. Here it says find the exact value of the expression, and it says tangent arc cosine of 3 over 5. And so what I think is important here is we set up a little diagram to kind of consider this picture. So if I go to the standard position, remember that cosine is adjacent over the hypotenuse. So if I put in a little right triangle here, and I say that the adjacent side here is 3 and the hypotenuse is 5, then the arc cosine of 3 over 5 will return this angle. I really don't care what that angle is because I'm about to be taking the tangent of that angle. Remember what the inverse trig functions do. They take ratios and they give you angle measure. And so this literally reduces down to the tangent of theta. And that angle right there is this angle right here. And again, I don't need to know what that is because the tangent says find the ratio of the y value to the x value. I already know what the x value is. It's 3. I just need to know what this y value is. Now we can use the Pythagorean theorem. We can go 3 squared plus y squared is equal to 5 squared. But hopefully by now you've seen, oh, this is a 3, 4, 5 right triangle. You can make that calculation if you want, but to save time, I'm telling you it's 4. I put my 4 in there, and that is my final answer. Okay there, folks, that's all I've got for today. So, the Star Wars fun fact of the day: in the original release of Star Wars A New Hope, there was no episode number nor the subtitle because the Fox distributor thought that it would be confusing for an audience to look for non-existent previous episodes. It was added after Empire Strikes Back when it was released in April 10th, 1981, and it would take until 1999 before episode 1 came out, which is a number of years later. All right, that's all I got for today, folks. You have a great day. Goodbye.